Assalamualaikum. Let's continue with chapter 3, periodic table. We look at 3.2, periodicity. Let's look at the overview for this subtopic. We have variation in atomic radii, isoelectronic species, variation ionic radii across period 2 and 3, ionization energy, successive ionization energy, electronegativity, and acid-base character of oxide. The learning outcome for this subtopic is at the end of the lesson, the student should be able to describe and analyze the variation in atomic radii across a period, across the first row of transition element, down a group. First, let's look at what is meant by periodicity. Periodicity is the periodic trend in properties of element. Atomic radii, so what is meant by radius, is equal to the half of the distance between the two nuclei of two adjacent identical atoms. From the diagram below, A is the distance between two nuclei adjacent atoms. The atomic radius of an element is determined by two factors. The first one is effective nuclear charge or Z, and the second one is shielding effect or also known as screening effect. Effective nuclear charge or Z is the net positive charge experienced by valence electron. The formula for effective nuclear charge or Z is equal to the number of protons Z minus the number of electrons filled at the inner shell. When the effective nuclear charge Z increases, the nucleus attraction towards electron becomes stronger. The nucleus pulls the outer electron closer, making the atomic radius become smaller. How to calculate the effective nuclear charge or Z? So let's look at the example given. We have three elements: fluorine, aluminium, and potassium. For element of fluorine, the electronic configuration is 1s2, 2s2, 2p5. Proton number of fluorine is 9, and the number of electrons at the inner orbital is 2. The number of electrons in the inner orbital we get from the inner shell, that is 1s2. So the effective nuclear charge for fluorine is Z equals 9 minus 2. We get positive 7. For aluminium, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Proton number of aluminium is 13, and the number of electrons in the inner orbital is 10. The inner electron we get from 1s until 2p6. And the effective nuclear charge for aluminium is 13 minus 10. We get positive 3. And for the element of potassium, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The proton number for potassium is 19, and the number of electrons in the inner orbital is 18. The inner electron we get from the inner shell, 1s2 until 3p6. So the effective nuclear charge for potassium or Z is 19 minus 18, so we get positive 1. Let's look at another two examples for the calculation of effective nuclear charge or Z. For element of fluorine and magnesium, that is from the same group of halogen. For element chlorine, the proton number is 17. First, we write the electronic configuration of fluorine. 1s2, 2s2, 2p6, 3s2, 3p5. So the effective nuclear charge of chlorine is proton number minus the number of inner electron, 17 minus 10, so we get positive 7. The inner electron from the chlorine atom we get from the orbital of 1s until the orbital of 2p, that is in the inner shell. The atomic radius of chlorine is smaller because the nucleus pulls the outer electron closer with a charge of positive 7. For element of magnesium, the electronic configuration is 1s2, 2s2, 2p6 and 3s2. The effective nuclear charge for magnesium is 12 minus 10. The inner electron from magnesium atom we get from the inner shell 1s2 until 2p6. So the effective of nuclear charge for magnesium is positive 2. The atomic radius of magnesium is bigger than chlorine because the nucleus can only pull the outer electron closer with a charge of positive 2. Let's look at the exercise 1. Rank each of set of main group element in order of decreasing atomic size. Briefly explain your answer. A. We have potassium, gallium and calcium. B. We have bromine, rubidium and krypton. So for element of potassium, calcium and gallium, elements of potassium, calcium and gallium are elements of the same period. It is the element of the same period because the electronic configuration for potassium, calcium and gallium ending with the highest principal quantum number n equals to 4. Across the period, from potassium to gallium, proton number will be increased, effective nuclear charge increased, hence the atomic size is reduced. So the arrangement for the size for the element of potassium is bigger size than calcium and calcium has a bigger size than gallium. For B, rubidium, bromine and krypton. For rubidium, bromine and krypton are elements of the same period because it has the higher number of n is equal to 4 for bromine and krypton, while for rubidium, the highest number of n is equal to 5. Bromine and krypton are elements of the same period, so bromine has less proton number than krypton, so bromine will have a lower effective nuclear charge compared to krypton, hence is larger in size. For rubidium, it has a higher energy level from period 5, so the inner shell increase, shielding effect increase, and the atomic size is bigger. So rubidium has a bigger size than bromine, and bromine has a bigger size than krypton. Shielding effect. Shielding effect is the second factor that determines the ionic radius. It is also known as the screening effect. It is caused by the mutual repulsion between electron of inner shell and the electron occupying the valence shell. It also occurs between electrons in the same shell but is less effective compared to that of electrons in the different shell. Lithium has the lowest shielding effect compared to sodium and potassium. Potassium has the highest shielding effect with more electron and higher number of shell. Let's look at the diagram. We have electron, inner electron at each of the shell, and the outer electron at the outermost shell, the positively charged nucleus at the center of the atom. So all the inner electron experience repulsion between itself and also repulsion between the electron in different shells. So the inner electron will shielding the outer electron from the attraction with the positively charged nucleus. The inner electron shields the outer electron more effectively, so the outer electron feel less attraction from the nucleus. From lithium to francium, the element is in group 1. The number of inner shell increase, the shielding effect increase, weaker attractive force between proton in the nucleus and the valence electron. The valence electrons are loosely held and making the size of atom increase. When we go down a group for element in group 1. The analogy for the shielding effect is atomic size is like the spot on a giraffe neck. The increasing atomic size as you go down a vertical group or family in the periodic table is similar to the pattern of increasing size shown by the spot on a giraffe neck as you go from its head down to the body. Let's look at exercise 2. Arrange the following set of atoms in order of increasing size. Explain. We have magnesium, beryllium, and calcium. So for magnesium, it has the higher value of N equals to 2. For magnesium, the higher value of N is equal to 3, and for the calcium, it has the higher value of N is equal to 4, and it is in period 4. Beryllium in period 2 and magnesium in period 3. These three elements is from the same group because it has the same number of valence electrons that is equal to 2. So these elements are of the same group. Moving down a group from beryllium to calcium, the number of shell increase. This will increase the shielding effect, hence the bigger the atomic size. So beryllium has a smaller atomic size than magnesium. Magnesium has a smaller atomic size than calcium. So the conclusion for this variation in atomic radii, when we go across a period, the proton number will be increased, effective nuclear charge increase, attraction between valence electron and the nucleus stronger, so making the atomic size become smaller. For down the group, when the number of shell increase, the shielding effect will be increased, attraction between valence electron and the nucleus will be weaker, and the atomic size will be increased. So we can see from the table, when we go across the period, the atomic radius increase. When we go down the group, the atomic radius become increase. Now we look at the variation of atomic radii across the first group of transition element. So from the graph shown that for the element of transition from scandium to zinc, the atomic radius of transition element is almost constant across the period. Why? Atomic radius or radii of transition element, it does not change significantly across the period. This is because the electrons are added to the inner d orbital. The 3d electron shield the outer 4s electron from the attractive force of the nucleus. Thus, the increase of nuclear charge, number of protons, is cancelled by the increasing of shielding effect caused by the additional inner electron. Therefore, the size remains relatively constant.